class, we are now on chapter 3.8. We're going to talk about energy. Energy is what we need in order to just, in our everyday existence. If we did not have food, we would not have enough energy to move. Energy is pretty much everything. We're going to look at different types of energy. Energy is the capacity to do work. Basically, an example is if you don't have food, you can't do work. So that you don't have the capacity, if you don't have energy, you don't have the capacity to do any work. Work is we need energy to do work, as simplistic as it may sound. Energy is the capacity to do work, makes objects move, makes things stop. Everything, all of that has to be considered work. Work is defined as a result of a force acting on a distance. A perfect example of this is a combustion reaction. We put gasoline in our cars. Gasoline is combustible. The heat that's given off is then allows the pistons to move, and with the pistons moving allows our car to move. So it's a chain reaction, but with work we get things done. So the behavior of matter is driven by energy, and understanding energy is critical to understand chemistry, because we use a lot of chemical reactions and we use the heat off of it, we use the energy, we use this and energy comes in different types of form: chemical, electrical, and so forth. Everything that allows us to have the life that we have today. Law of conservation of energy. So like matter, which we just covered, the law of conservation of matter, energy is also conserved. That means that you cannot destroy or create energy out of nothing. So all these movies that we see where things can be created out of nothing, that doesn't exist. Something's always got to give somewhere. So in this case, energy is neither created nor destroyed, even if we don't always see what's happening. The total amount of energy is constant. So energy can be changed from one form to another. So just because we don't see where all the energy is going, it may be changed into another form, and that's why we're not able to visually detect it. Energy can be transferred from one object to another. Energy cannot be created out of nothing, and it does not vanish into nothing. So there are two different types of energy I want to talk about here. There is kinetic and there is potential. Energy makes objects move. Again, is defined as the ability to do work. There's two types: kinetic energy, which is the energy of motion, and potential energy, which is energy possessed by an object because of its position. So a perfect example is this nice little gift that I found. Now, excuse me, if you look at it, when one energy goes up, the other energy automatically goes down. And that's because energy cannot be created nor destroyed. It gets changed into another type. So there's a numerical value that is not posted here. And regardless of the value, let me see how I explain this. The value, the numbers will change, but the numeric value of the overall energy will stay the same. That's because it will adjust. These numbers will adjust, but the total value will always stay the total value. So kinetic energy is the energy of motion. That's the pretty much easy one. If you follow the green, you can see right here, that's motion. And then as it goes up, the motion goes down. The energy is not as strong, it's not as full. That's potential. That's because of the object of its position. That means that exactly what it's saying. It's potential energy, and it's increasing as it gets to the top. It's at its max, and it releases that energy, and it changes into energy of motion. But the value here, so let's say on it, let's pick a number. The total value here is 100. So let's say this is 75, that's 25. Now that's 75 and this is 25. So hopefully you guys understand that's what I mean. It's a total number. It does not go away. You can't create something out of nothing. There's a value, and it has to be respected in this sense, and you will see that the potential and the kinetic energy values will either increase or decrease to make sure that value stays consistent. A dam is a perfect example of a potential energy. If this was to break, do you understand how much energy that would release? That's a lot of energy. That's why this would be a potential energy, because of its position. Kinetic energy, energy of motion, that should be easy. If you're moving, you've got kinetic energy. Anything, swimming, flowing, water over a dam, working out. If you are in motion, you have kinetic energy. Potential energy would be you, basically a perfect example, the top of a roller coaster. That roller coaster will then have potential energy right there, and then it goes down, and it turns into kinetic. Potential energy is energy stored for use at a later time. If you eat, you are storing potential energy, because that's going to give you the energy to use later as kinetic. So if you run, you want to eat something and then you're going to go for a run later, that's what you're probably going to use to get you the energy to run. It is determined by position of an object or the chemical composition of a substance. What that means is something like gasoline. It's got potential to give off its energy, but until it's flammable or combustible, it hasn't given off that energy yet. Examples are the following: water at the top of a dam, a compressed spring, chemical bonds, and gasoline, coal, or fuel. That's potential energy because we need all those. And once they're used, they are now allow us to have motion, energy of motion. The water at the top of the dam has potential energy because of its position, meaning if that dam breaks, if you guys have ever been to, what is it, Hoover Dam, I think? It's massive. And if that dam was to break, all that water would, it's amazing what could happen. So let's take a look at some examples. Identify the energy in each example as potential or kinetic. So rollerblading, is it in motion? Yes, it is. So, I have all the answers, so let's just break them down. Kinetic. A peanut butter and jelly sandwich, that's food, so that's going to get stored, and then it will be converted into kinetic energy. That's potential. Mowing the lawn is kinetic, you're in motion. And gasoline in a gas tank, that's like food, we need gas or the car will not go, so that's potential. Different forms of energy. The total energy of a sample is the sum. So this is that number I'm telling you. If there's a certain number on that roller coaster, the kinetic and the potential will change to adjust, but that total will never change. So the energy associated with motion and the energy associated with position of composition, that is the sum, and that will make the total energy of a sample. We also have electrical energy. That's energy associated with the flow of electrical charge. Thermal energy, that's heat. The energy associated with random motions of atoms and molecules in matter. Chemical energy, a form of potential energy associated with the positions of the particles that compose a chemical system. So there's different forms of, and there's more forms of energy than what's even listed here. Energy is in so many different forms. Now, energy has units, and there's 2 units. There's a few units on here, but there's 2 I want to, do I have 2? No, I have 3 units listed on here. But there's 2 that you need to pay attention more than even the third one. The first one is joule. And if you go on to Chem 111, you will have these in your sleep. You're not going to get out of that chapter with thermochemistry. The joule, it's a small j, but if it's by itself as a unit, it's a large j, and it's pronounced joule, like jewelry, or kilojoules is what's used. And 1 kilojoule equals 1,000 joules. The other unit is calories, a small c, and 1 kilocalories equals 1,000 calories. Those have to do with units of energy, and definitely in Chem 111 you become very familiar with this. The calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. What that means is how much energy does it take to increase that 1 gram of water 1 degree. So that's how we use calorie. Now, a related energy is nutritional. It's a big C. It's a capital C. And that equals, which I wish they had thought of something different, but a capital C is equivalent to 1,000 little calories. So 1 large C equals 1,000 calories. And so 1 kilocalorie is equal to 1 large C calorie, and both of those are equal to 1,000 calories. That's more nutritional. The food content on the side of a box, that's a nutritional, that's what that one tends to be used as. The kilowatt per hour, this is 1 kilojoule per second times 3,600 seconds in an hour. Don't get caught up on that. That's just, don't worry about that. It's in your book, I'm saying it, but it's not really something I'm going to focus on. Focus more on the joules and calories above. The average cost of residential electricity in the United States is about 12 cents per kilowatt per hour. Let's move on from that. The one I want you to walk away from this slide, and it's very important that you understand that cal and joules are units of energy. They are the energy that we will be looking at later on, and you'll have to do some things with them in lab as well. 1 calorie equals 4.184 joules, and that isn't exact, so you would not have to factor that in to a sig fig. So you definitely should know this. And then this is in your book. It also gives a chart for energy conversion factors if you would need to use them in calculations. And now let's do a problem. So a candy bar contains 225 large C calories of nutritional energy. How many joules does it contain? So we have to do two conversions here. We have a large C, so we need the conversions of 1,000 calories equals 1 large C cal. This is from another book, so don't pay attention to that. It might be, oh, maybe it is there. It is there. I did add that. And then the conversion I want you to know, which is also in that printout that I've given you, is 4.184 joules equals 1 cal. So we need to use these in order to go from large C cal to joules. So we are given 225 cals, but we need to get to joules. So we need a stepping stone. We need to go from large C cals to low C cals and to joules. And we have a conversion for it here, and we have a conversion for it here. So now we should plug everything in. We have 225 cals. This is a conversion. We do not use this. This is also exact, so we don't use it. The only thing that will factor in here is this number. So 3 sig figs. In this case, you would have a lot of zeros, or you can write this in scientific notation, which is done here. And this is 9.41 times 10 to the 5th joules. That's it.